Well, friends, today in this session, power plant boilers, we will be discussing about the fuels and coal combustion, oxygen, CO2 percentage, and excess air. So, let us start. The fuels generally, four types of fuels are used in coal based thermal power stations: light oil, furnace oil, LHS, and pulverized coal, and LPG and CNG or gaseous fuel. Out of these first two, they are liquid fuels, and rest the third one is the solid fuel, and fourth one is the gaseous fuel. Liquid fuels and gaseous fuels are generally they are used for initial starting or for the stabilization of flame. The fuel properties, liquid fuel properties have the following fuel properties: specific gravity, LDO specific gravity is 0.85 to 0.87. Furnace oil, the specific gravity is 0.89 to 0.95, and LHS, the specific gravity is 0.88 to 0.98. The viscosity, the liquid fuel viscosity, it is specified in Stokes or centistrokes, Redwood, Egler, or Sebold. It depends on the temperature. Viscosity decreases as temperature increases. Viscosity influences the degree of preheat required for pumping, burning, atomization, and it may cause carbon deposits on burner tips. The flash point is also one of the properties of the liquid fuel. Pour point for pumpability, and the specific heat is also a property which will determine how much steam will be required for preheating. The heat value and the sulfur percentage of liquid fuels. The kerosene has the GCV of 11,100 and the sulfur percentage is 0.5 to 0.05 to 0.2. The LDO has got the GCV as 10,700. The LHS has got the GCV as 10,600. The sulfur content in both these, in LHS it is more than 0.5, and in LDO the sulfur content is 0.5 to 1.8. The diesel oil and furnace oil, they have the GCV as 10,800 and 10,500. The sulfur content varies from 0.05 to 0.25 or 2 to 4. The storage, about the liquid fuel storage, the storage sizing is generally important, and generally it is for 10 days requirement. The capacity of the tanks, it depends on vertical above ground with bund walls. Generally it is vertical above ground. The cleaning, generally the cleaning is done annually for heavy oil and 2 years, once in 2 years for light oils. Now all leaks from joints, flanges and pipelines, they must be arrested, as loss of one drop of oil every second may cost over 4,000 liters per year. These are the storage tanks for the liquid fuels, and the storage tanks you can see the bunds are provided there. So if any leakage is there in the tank, the oil can be collected in the bunds. The contaminations, regarding the liquid fuel contaminations, they are checked by means of the strainers. So core strainer of 10 mesh is fitted at the entry pipe to the storage tank for rags, cotton waste, loose nut bolts, screws, etc. Then 40 mesh strainer between the service tank and the preheaters, and 100 mesh strainers between the heater and the burners. The solid fuel, that is coal, it is graded into A, B, C, D, E, F, G like that, and grade A is exceeding 6,200 kilocalories, whereas grade G coal is having an thermal value as 1,300 to 2,400 kilocalories per kg. The typical analysis of coal, when the coal is received, the typical analysis, proximate analysis is done, and generally for the Indian coal, the moisture percentage is 5 to 5.98%, and in imported coal it is around 9.5%. The ash percentage in Indian coal is 38%, whereas in imported coal it is around 14%. The volatile matter is 20%, whereas in imported coal it is 29.79%. The fixed carbon is less in Indian coals, it is 34.69%. But in imported coal it goes to around 46%. The significance of these parameters: the fixed carbon, it is the solid fuel left in the furnace after the volatile matter is distilled off. The volatile matter, it contains methane, hydrocarbons, hydrogen and CO. This is also known as the index of gaseous fuels present in coal. The volatile matter increases the flame length and helps in easier ignition of coal. It sets minimum limit on furnace height and volume. It influences the secondary air and its distribution. It influences secondary air oil support also. Ash content. It reduces the handling and burning capability. It increases the handling costs. It affects the combustion and boiler efficiency. It causes clinkering and slagging. The moisture content. It reduces the heat content per kg of coal. It increases the heat loss due to evaporation and superheating of vapor. It helps in binding fines. It aids in radiation heat transfer. The sulfur content. It affects clinkering and slagging tendencies. It corrodes chimney and other equipment in flue gas path, aerator, economizer, etc. because of formation of acids. It limits the exit flue gas temperature for the above reasons. It affects the heat lost in flue gas. It increases the cost of maintenance. The proximate analysis of coal, what is the process? The process is, first it is grinding coal to fine powder and then weighing. Then number 2 is drying coal in atmosphere and weighing. Number 3 is drying the coal in nitrogen furnace at 110 degrees centigrade for 1 hour and then weighing. It is then further subjected to 925 degrees centigrade for 7 minutes in the nitrogen furnace and weighing. Then fifth one is further burning the coal totally with oxygen in the furnace to ash and weighing. Generally 1.5 hours it requires. And then 6 is noting down the proximate analysis. How the moisture and volatile matter is calculated. The difference of weight between 1 and 3, the powdered coal, and after drying the coal in nitrogen furnace up to 120 degrees centigrade gives the moisture present in the coal, that is N. The difference of weights between 3 and 4, that is dried coal, and subjecting it to 925 degrees centigrade in nitrogen furnace gives the weight of the volatile matter in the coal, that is known as Vm. Ash in the coal is denoted by ash and is given by the weight at 5. Further, the difference of weights 4 and 5 gives us the fixed carbon in the coal denoted by C for the calculations of ultimate analysis. The procedures may slightly differ from place to place, but generally they are carried out as per ASTM 3. The ultimate analysis of coal is derived from the proximate analysis. So the relationship between the proximate and ultimate analysis is percentage of carbon is equal to 0.97C plus 0.7 into bracket Vm minus 0.1A bracket close minus M into bracket 0.6 minus 0.1 M. Percentage of H is as per the formula given there. Percentage of N is also calculated as per the formulas given. Now in these formulas, C is the percentage of fixed carbon, A is the percentage of ash, Vm is the percentage of volatile matter, and M is the percentage of moisture we got from the proximate analysis. The typical values of ultimate analysis of coal for Indian coal and for Indonesian coal, it is given in the table. You can see the table. The gross calorific value of Indian coal comes to around 4000 kilocalories, and for the Indonesian coal it is around 5500 kilocalories per kg. The energy released by the constituents of coal. Now for calculation of GCV and NCV, we need to analyze the fuel and get the constituent of fuel on weight basis. So based on the enthalpy of formation, we may estimate the calorific value of fuel. The equations for the energy are C plus O2 is equal to CO2 plus 8137.5 kilocalories per kg of carbon burnt. Hydrogen plus 0.5 O2 will be equal to H2O, that is moisture, plus 28,905 kilocalories per kg of hydrogen. Then sulfur plus oxygen, S plus O2 is equal to SO2, and it will release 2181 kilocalories per kg of sulfur. So depending on this, the GCV can be calculated. So GCV, for the simplicity, we consider a fuel containing carbon, hydrogen, nitrogen, sulfur and oxygen as the 86.5, 12%, then 0.9%, 0.2% and 0.4% respectively. Then the GCV can be calculated as per the formula. And you will see from the GCV 10,497.2 kilocalories per kg. The NCV of the fuel can be calculated, which comes to around 9,866.5 kilocalories per kg. The comparison of chemical composition of various fuels. Now, fuel oil is liquid fuel, coal is solid fuel, and natural gas is the gaseous fuel. So the constituents and the chemical composition is given here: carbon in fuel oil, hydrogen in fuel oil, sulfur in fuel oil, oxygen in fuel oil, nitrogen, ash and water in all this has been given. You can compare from these. The burning of fuel. Now the required rate of combustion is dependent on the heat energy requirements. What are your heat energy requirements? For 500 megawatt boiler, the rate of coal combustion roughly is around 300 tons per hour at full load. For 210 megawatt boiler, the rate of coal combustion is approximately 140 tons per hour at full load. So the combustion system is such designed for achieving this rate, that too within the optimum furnace volume. Impact of CO formation. In perfect combustion, carbon is converted into CO2, but when there is deficit of oxygen, CO is generated as below. So C plus O2 is equal to CO2 plus 8137.5 kilocalories per kg of carbon, wherein if only carbon monoxide is generated, then the equation would be 2C plus O2 is equal to 2CO plus only 2430 kilocalories per kg of carbon. So this indicates that a loss of around 5707.5 kilocalories of heat per kg of carbon burnt in compared to the carbon burnt with conversion as CO2. Hence CO generation must be avoided with calculated excess supply of oxygen for combustion. Now what is combustion? Combustion definition. Combustion is the rapid oxidation of fuel accompanied by the production of heat and light. Solid or liquid fuels must be changed to gas before they burn. Heat is required to change the solids and liquids into gases. Most of the air, 79%, is nitrogen. Nitrogen reduces combustion efficiency by absorbing heat from combustion and reduces the heat available for transfer. It increases the volume of combustion byproducts. Combustion at high temperatures may produce oxides of nitrogen, which are toxic pollutants. The rate of combustion. Combustion takes place only when the fuel is in contact with oxygen in air and sufficient ignition energy is available. Intense radiation from the flame provides ignition energy. Oxygen is available from air supplied from primary air and secondary air system. Rate of combustion is decided by the rate at which oxygen from air combines with the fuel particles. Combustion system design. What are the issues? Combustion system is designed to obtain high rate of combustion carried out in a limited furnace space, minimum heat losses, then ease of operation and maintenance of the combustion system, the safety of main and equipment, and controllability of the combustion process. So please like and share.